Hello, welcome to some more chemistry. What we're going to have a look at today is continuing where we left off last time, and we'd looked at the alkali metals, and today I want to start having a look at the halogens, the trends going across the periodic table. I want to have a look at transition metals and start looking at bonding. So let's have a go. Halogens. Right. What are they? Well, the halogens are here chlorine, bromine, and iodine. We've also got fluorine as well, but we tend not to use that in the lab. There's a very good reason why we don't use fluorine in the lab, and that's because it's so dangerous. So we've got fluorine, chlorine, bromine, and iodine are our four halogens to sort of have a look at. Now, when we looked at the alkali metals, we looked at lithium, sodium, and potassium, and we found that they got more reactive as we went down through the group. We also looked at magnesium, and we looked at calcium, and we found that was also true. But it's not true of these. The halogens, they get more reactive as they move towards the top of the periodic table. This does mean that if we have a look at our periodic table, and we'll just make a really crude periodic table here, we find that the periodic table shows that the most reactive metal is going to be cesium down in this corner, and fluorine up in that corner. If I just have a look at the periodic table then, to sort of see this, then cesium down the bottom here is the most reactive metal, more reactive even than francium, and fluorine is the most reactive non-metal. So why is this? That's not making any sense. Why should it be going one way for one set and the other way for a different set? Well, we need to understand why this is. So let's have a quick look at, first of all, some of the properties and why it might be so. We've got fluorine, most reactive. And if I look at this in terms of its shells, it's got 2 electrons in the inside layer, and going around the outside, it's got 1, 2, 3, 4, 5, 6, 7 electrons. Now, if we compare that with something like lithium, that's got 1 electron in its outside layer, and it's relatively easy to remove that, and that's why it's very reactive. Fluorine, on the other hand, is equipped with 7 electrons in this outer layer. So to get this to react by taking on an extra electron means it's got to make it go on by losing 7 electrons. It's got to lose 7, and that's a lot of effort to lose 1, then 2, 3, 4, 5, 6, 7. But it's easier for it to accept a new electron. Now, if we go across the periodic table, and I start with lithium, and then beryllium, boron, carbon, nitrogen, oxygen, and fluorine, we've got here 3 protons, 4, 5, 6, 7, 8, 9. So this is the number of protons. It's building up by 1 each time. But these electrons in this shell don't get any further away. So this positive charge increases, and this shell just starts to get more and more electrons in. So these are at the same distance away from this point of view. So if we look at something like lithium, my outside electron's quite a way away. But if I look at fluorine, these electrons have been brought closer to the nucleus. There's more charge going on. So as we go across this period, so the atomic radius, it is decreasing. And what does this mean? It means that the strength of holding on to these electrons is increasing. So much so that when we get to this side of the periodic table, rather than losing electrons, these substances generally prefer to gain electrons. I'm not saying you can't remove the electrons, but it gets significantly more difficult. So the charge here is increasing, and if we look at fluorine and we compare this with chlorine, the same sort of thing is happening. So if I look at my atom of sodium, we've got here electrons in the way of the nucleus, and this is called electron shielding. And as we look at the electron shielding, it's increasing. And if we go down and look at potassium, there's yet another layer, which is making it easier for this electron to be removed, because there's more other electrons in the way, shielding this electron from the nucleus, the strong positive charge that's attracting it. On the other hand, we're looking at fluorine, and there we look at chlorine. We've got more charge, so less atomic radius, so we're bringing these things in. So these are more attracted by this strong nucleus. This has got so much charge and so many electrons. The chlorine's got more charge, but the electrons are further away. So the fluorine is more reactive than the chlorine, and so on. Well, let's see how this ties in when we look at the properties of the halogens. Let's take a substance, and what we're supposed to have a look at when we have a look at these is simply having a look at some of their properties. We find that fluorine is a gas at room temperature. and quite a toxic and reactive gas it is too. It reacts with nearly everything. A classic experiment with fluorine is to react this with something like charcoal. Just put a bit of fluorine gas, you just sort of put it next to some charcoal, and immediately sparks fly as it sort of bursts into flame. And charcoal doesn't burst into flame very easily with most things. So fluorine, a gas, very reactive. Chlorine, again, is a gas, and it's been used as a poison gas. It's used to kill bacteria, and effectively it does so. Bromine, at room temperature, this is a liquid. And finally, iodine is a solid. What can we do about colours? Well, the fluorine is pale blue in colour. The chlorine, a quite convincing sort of green, a pale green in colour. Bromine is brown and iodine is black. We can think of these getting, if you like, darker as we're going, from pale blue to sort of pale green to brown to a sort of bluey black colour. As for the properties, well, what we do is we take some chemicals like potassium iodide. If I take some potassium iodide and I bring near it some bromine, and we typically do this by dissolving bromine in water. Bromine is again very good, like chlorine, for killing bacteria. So it's quite a harmful, noxious substance. Bromine is the stuff that boys often, tends to steal out of a chemistry lab, and they try and let it off as a stink bomb. Yeah, it's very effective as a stink bomb. It's also very toxic, and so it doesn't usually achieve what they set out to do. Yeah, it stunk the place out. Yes, they probably had to evacuate the place. And yes, they probably got it arrested and in a lot of trouble. So bromine, quite reactive, quite noxious, quite dangerous. Iodine is at the bottom of the table, and iodine is still used as an antibacterial chemical, bactericide. If I take iodine in the form of potassium iodide and we react this with bromine, then we get made potassium bromide, plus we get iodine gas, or if it's in liquid, maybe iodine dissolved in some water. And this isn't balanced, is it? Looks horrible. So I've got to try and balance this. I've got two iodines on this side, therefore I've got to have two iodines on this side. That means two potassium iodides, which means I've got to have two potassiums here. We must have two potassiums there, which gives me two bromines, which balances beautifully. So if I take potassium iodide plus bromine, we get iodine given off. If we do the converse reaction, if I take two lots of potassium bromide and I react this with iodine, we get no reaction. Okay. If it goes this way, it's not going to go that way. Let's take a different substance. Let's take this time some potassium bromide. And this time I'm going to put some chlorine gas with it. Now the chlorine is better if we dissolve it in water. So chlorine water with potassium iodide solution, and then it works and we produce 2 lots of potassium chloride plus some bromine gas is given off. And we can tell the reaction's taken place because the colour of the gas or the liquid here is going to go from pale green to brown. If I do the converse reaction, I take 2 potassium chlorides and I add bromine to this, then no reaction. And if I'd taken my potassium chloride and I'd added iodine to it, we'd have also seen no reaction. We can do another one here. We can take potassium iodide and I can react that with chlorine, and this gives me potassium chloride plus iodine water, or iodine given off. There we are. That wasn't very good. I didn't show you what I was writing. Right. So from this, we can determine that chlorine is more reactive than bromine, which is more reactive than iodine. And from this, we can probably deduce that fluorine is going to be more reactive than chlorine. The last of the halogens, astatine, doesn't exist. And nobody's seen it. So again here, it's something we would have to try and guess about. So that's giving us an idea about the halogens. We've got the properties of them. Well, they're gases for some of them, fluorine and chlorine, then bromine a liquid, iodine a solid, so they've got fairly low melting points and boiling points. The bromine you can turn into a gas fairly easily. Iodine's rather peculiar, and if you want to take some iodine and you want to heat it, then it sublimes. In other words, it turns straight from a solid to a gas. And this is one of the interesting features of iodine. Poor conductors of heat and electricity. Yep, they certainly are. They are typical non-metals, and they don't conduct heat very well, and they don't conduct electricity at all. And we've looked at the colours. Okay, so there are our halogens. We've also looked at here some of the trends that we are seeing. If I take some of these substances, just changing the piece of paper for you. If I take across the period. Let's go from lithium to beryllium. Not really an experiment that we've actually tried. Lithium's commonly available. Beryllium, on the other hand, is not particularly nice. It's actually quite carcinogenic, and getting hold of beryllium is quite difficult. But I do have here a sample we can have a look at. And it's the only time I've ever seen beryllium. And I don't know if I can turn that light off for a moment. Just turn it round. Can you pull? There we are. Slightly easier to see. Now, beryllium is very toxic, so we're not going to look at that one. So rather than go across that period, which is quite difficult, let's look at the next period. And I'm going to look at sodium and magnesium. We did this experiment last time that we took some sodium, put it in some water, magnesium, put it in water, and this one was super reactive, and this one wasn't really. And if we go across the period, we can see some other things happening. So my next element across is aluminium. Magnesium does react, that's only with water, but with other things it burns quite brightly. Aluminium, much more difficult to try and get this to burn. Trying to burn aluminium can be done, and it's normally done not with taking some aluminium foil, but by taking something like fine bits of aluminium. And trying to get that to work is quite fun. And there's a lovely experiment called the Thermic reaction. And we start off with a magnesium fuse, and if you try really hard and well, you can get the aluminium to react with iron oxide. And the aluminium burns and takes the oxygen away from the iron. Very effectively, I might add, in that the iron actually melts. And it's often used in welding. Railway lines come to mind, and if you want to have a look at some videos there, you'll find the Thermic reaction on trying to do some welding of railway lines together. Quite interesting. Maybe frightening as well. I'm not going to do the Thermic reaction. It's pretty hard to get going all the time. It's not one of the most reliable ones to get going. And I want to compare that with magnesium and sodium. So sodium, most reactive, then magnesium, then aluminium. And going across my periodic table, then we've got to aluminium, then we get to silicon. Well, not that bad. Phosphorus, sulfur, and then chlorine. So these substances here, well, what can we say about them? Well, we can say the metals here are gradually getting less reactive as they go across. The same is not true when we get to the non-metals. Over the other side of the periodic table, where we get the non-metals, they are tending to get here more reactive. Going across here towards chlorine, which is quite reactive compared with perhaps some of the other substances. So we look at some of the trends here as we're going across the periodic table. And what we notice is several different things. Right, so what trends can we notice? Our trends are, we've got reactivity in groups. Generally, in the metals, they're getting more reactive as they go down. In the non-metals, it's going the other way. They tend to get more reactive as they go up. Going across the period, then we're seeing changes going along from metals to the ones that can't make their mind up, the metalloids, to the non-metals. And we've already explained some trends why group 7 is different. And it's the group of halogens. We can call it group 7. And we find that the size of the atom, well, they decrease as they go across and they decrease as they go up. And so this is fluorine, the most reactive item. The atomic radius is here going to decrease, and this way it's going to decrease. The shielding. The shielding here increases as we go up to fluorine. And we can see that the nuclear charge, this increases as we go because the electrons are nearer. So this gives us an idea about some trends. Let's look at then the next item on our list, which is some transition elements. And to do this, I think it's probably going to be easier if we actually have a look at a few of them. So let's go and do that. So let's switch over to this other camera and we'll move it out so we can have a look at a couple of these items. My son brought me a couple of these elements to have a look at. He's only brought me copper and zinc. There's another pile which he's going to go and get now, which will bring me a few more while we have a look at some of these. Right, so copper. There we are. A piece of copper, quite a nice sort of lump of metal, typical sort of salmon pink, orange colour as it gets sort of more older and tarnished. Right, the first substance I'm going to have a look at is that of zinc. This is zinc oxide. And zinc oxide is a boring, classic sort of white powder here. And you can just see there that it's sort of just a white powder. Nothing exciting. The zinc compounds tend to be white, unlike the copper. Now I've got here two bits of copper, and I've got copper 1 oxide, which is called cuprous oxide, and I've got copper 2 oxide. Now let's see if I can just make the camera a little bit higher here. And Paul's going to adjust so we can see easier down into the chemicals. And this is the one that you may be the most familiar with. This is copper 2 oxide, and this is the black colour of copper oxide. And Paul will sort of show that to you. The other copper, this is copper 1 oxide or cuprous oxide, instead has a very bright sort of reddish colour. What a deep reddish colour here. So it looks very different. And this is because this is copper 2 oxide, so formula copper CuO, whereas this substance has a different formula, which is Cu2O. So suddenly we met some new chemicals, and they've got slightly different properties. Some of the transition elements aren't +1, +2, +3, but they can have several different oxidation states. And this causes a fair amount of confusion. Let's have a look at some more copper. This is one that you're probably fairly familiar with. Most people have seen copper sulfate. Either the dark blue crystals, when it's sort of hydrated properly, or we've got some other crystals which are sort of less more defined. So here I've got some more copper. Let's just pour this in here, and what I want to do is get out a crystal here of copper and pull zoom in here. And you can see it's quite a nice sort of little crystal. These are quite hard to grow, and probably one of my favourite experiments is actually trying to grow crystals. I've always been fascinated with these crystals, and these are sort of diamond in shape, but flat. So we've got some smaller ones which aren't so easy to see. But in here I have got a couple of larger ones. And where the other copper has gone, you can see better that these are sort of diamond in shape. So this is all crystallised at the bottom of a jar of copper sulfate. So there we are, copper sulfate, blue colour, and the more hydrated it is, the bluer the colour. So we can see that one quite clearly. Copper sulfate is not particularly nice. Here, other danger, and it's very toxic to most life. So not particularly nice. This is copper sulfate. Copper sulfate, however, occurs in, as I said, another form. And this is anhydrous copper sulfate. And you see, again, a very different colour. This one contains water, and the anhydrous doesn't contain water. And when it's newly made, it's really quite white. And this, you can see, is not quite white. You might see it's a slight blue colour. And this is where it's basically going off. A little bit of water in the atmosphere has got in here. And if I need to use this, then I need to heat this before I use it, and then it turns white again. That's copper sulfate. I'll show you a couple more copper substances. This is copper carbonate, and we see this sometimes on roofs of buildings, because if we take a piece of copper and leave it in the air, it'll go black, react in the air, make copper oxide, and then it reacts to form copper carbonate, which is this lovely green colour. You often see green colour for some roofs of some buildings. So it reacts with the carbon dioxide in the air. This is a good ore of copper and used in quite a few experiments in the lab. This is copper nitrate, dangerous to the environment. This one is flammable and corrosive. Let's have a look inside. And there we've got some lovely dark blue crystals of copper nitrate. It absorbs water quite naturally. So it's hygroscopic. I'll put the lid back on and stop it doing that. Lost the one I was looking for. There we go, copper chloride. This, I think, is beautiful. It forms beautiful green crystals. But when you dissolve it in water, it makes a blue solution. Again, this one, highly poisonous and dangerous to all living organisms. Not particularly nice. Right, I think I'll stop looking at those. Let's move on from the copper and those, and we'll have a look at some other substances. I've got one other here in the family of the copper group. The family here. I've got these away so I can get out. This is silver nitrate, probably one of the most expensive chemicals that I own, and I don't own an awful lot of this. It's flammable, it's corrosive, it's dangerous to life. It's in fact a sort of a grey powder you might be able to see inside there. Paul's frightening you. Yeah, you see in there? Yeah. And this stuff is what goes in socks. I've seen a few socks and they have silver in them to try and kill off bacteria. I've got a few more substances to have a look at. I've got some nickel. I've got some cobalt. I've got some iron. Let's have a look at a few of those. There we are. Manganese. Vanadium. I'll have a look at some of these. Right. Most of them come with warnings on them for being particularly dangerous. Of the most dangerous, I suppose, nickel is one of the most dangerous. Here we are. This is nickel sulfate. This is nickel nitrate. They're even pretty dangerous to open up, but we'll have a quick look for you. This is nickel sulfate, and it has really beautiful coloured crystals here. And for my nickel nitrate sulfate here, the experiments usually result in just us having a quick look at it because it is so toxic. Nickel nitrate. Not as exciting to look at, not as pretty a crystal, but quite nice. We're noticing something in common here, that these substances are coloured. We've got nickel there, they tend to be greens, the coppers were blues-ish, and iron here, this is iron chloride, and particularly this is iron 3 chloride with water, and it's this sort of mustard colour. Compare that with perhaps some iron sulfate. And iron sulfate is this sort of, I don't know what colour you try and just describe that as. It's got a pinkish tinge. Compared with iron sulfate here, which is iron 2 sulfate, and that is sort of a greenish tinge, definitely a different substance. This for young ladies is often made in tablet form if you want to try and take some iron tablets, and that's all it is, just that chemical. Cobalt, I've got a couple of cobalts to have a look at. But before I do that, I found iron nitrate. I had lots of iron nitrate. And iron oxide. Iron nitrate. Nice pink colour. Beautiful pink crystals. But when they get wet, they form an orange, sort of brown orange solution. Iron oxide, the familiar colour of rust. Right, now let's go on. I'm going to have a look at some cobalt for you. This is cobalt nitrate, and it's sort of a browny, sort of dark black crystal. Let's see. Lid back on. Many of these are hygroscopic. Cobalt sulfate, on the other hand, less hygroscopic. There's still this browny colour. So there's our cobalts. Not completely, we don't have a look at probably my favourite. This is cobalt chloride. And this is this dark red colour. Couple more to have a look at. We'll look at some manganese. We've got manganese dioxide, and this is a black colour. Not very exciting. And manganese sulfate, on the other hand, a beautiful sort of pink powder. So quite different. And the last of these is vanadium. This is vanadium oxide, and it's sort of a browny black substance. So what can we say about most of these transition metal elements and their compounds? Well, the elements, they are typical
metals. We think of iron, we think of copper. Probably metals that you are fairly familiar seeing. And they are really typical safe metals. I'm just going to do one thing before I finish, which is the important bit, which is washing my hands, because I probably did get some of the substances on me, and it's a case of having to try and wash my hands to make sure that I get rid of any of the chemicals that could have stuck on there, because the last thing I want to do is to actually then put any of those in my mouth, because they're all fairly toxic. Right, let's go and have a look at some of the facts.
So what can we say about transition elements? Well, fairly easy. Transition elements, then, they form coloured salts. Going across, we start with scandium, which I haven't got, vanadium, titanium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. We've looked at some of these. I don't have all of them. I do have some chromium compounds which I didn't get out. Titanium, I've only got some titanium oxide, which I didn't show you because that's white. Scandium compounds are white. Zinc compounds are white, except for zinc oxide. Zinc oxide's a really interesting one in that it is white, unless you heat it, in which case then it's yellow. And I haven't really got time here to try and show you that now. Maybe another time. So all of these have got coloured salts. We look at their chemical properties, and they are, well, let's look at physical properties first. The physical properties, they are, if you like, your typical metals. They're hard. And they're strong. They conduct electricity. They conduct heat. They're relatively heavy in that they have all got fairly high densities. And if you want to try and melt any of these metals, then we find that they've got high melting points and boiling points. The compounds of these, well, there are just a few things that we need to try and know. Copper, they tend to be blue. We looked at nickel. They tend to be green. Chromium, we didn't look at. These range here from dark green but also potassium dichromate, lovely sort of orange colour. Manganese, we looked at that, that was either pink or black. Iron we saw was yellows, greens, reds. Where you can have a look at the different colors of vanadium, and we'll put a link in the description to allow you to go and have a look at the different colors of vanadium. Vanadium starts off as yellow, then it goes to blue, and it confuses most students immensely because they all tell me it goes green, and I say no, it's gone from yellow to blue, and they argue and they say no, it's green, sir. And I say, but what happens if you mix blue and yellow together? And they go, it's green. I said, that's right, it's because it's blue. And they look at me funny. Then the blue goes on to green, and the green goes on to violet. So quite an interesting set of colors. It's quite a long experiment to do, and it would take a full hour to have a go at doing it, and it's a little bit shorter video as I've gone through, so we'll put a link in the description so you can have a look at that. So that's most of the ideas of the halogens, something across the periods, and then something on the transition elements. Next time, we'll have a look at structure and bonding, and we'll have a look at how all of these elements join together and fit together and make interesting sort of different compounds. I'll see you then. Take care. Bye-bye.